Okay, how are we on? Right. Well, thank you, faithful few. We're at the second part of the revision lecture now for those who are listening online. If the first one didn't record, I severely apologise. I'm sorry. But something seemed to have gone wrong at the end, so we'll just see how it turns out. If it did, then ignore that. So, all right. Yeah, it's hard talking to future students. So, in the previous one I talked about it's my way of organising my thinking about statistics and what goes where if I organise it spatially, and also some advice about the stock sentences you need to say to interpret stuff, and what I would put on a cheat sheet about any particular hypothesis test. Has anyone actually got that thing that Ben gave out in the tutes with the table at all?
Was that the what he told you to write?
Sorry?
Was that like a handout, or was that what he told you to write?
I'm not sure what Ben said. Yes, he's holding a tute on Monday in the morning tute time. So I'll have a slightly different perspective than him, but that's good. That's the reason why you have different teachers. Technically, I'm not actually involved in the teaching of Stat Prac I at all. I just help the people who turn up. So, okay, so I did go through the lecture slides and write down all the hypothesis tests I could find. And I'm going to run through them and talk about how I think about them. And I'll try and do this list that I made. So the first one is the Z-test for a mean. Okay, and that was the first one that you saw in the lectures. And it's actually the one that's never used in practice. It's the one that they use in a statistics course to teach you how hypothesis testing works, but you never actually use it in practice usually. So it's very unlikely for it to be in the exam, but as Rob said, anything could be in the exam, so we do need to talk about it. So the Z-test for a mean answers a question of this type. Is the mean of some variable equal to some number? That's what the question is like. Okay? And the most common place to see it is when you say, is the mean weight of a packet of nuts equal to what it says it is on the packet? Okay, that's the most common place you'll see it, because that's where this sort of test is actually used. Okay? So So I'm going to skip the parameters because I want to draw you the picture that I would normally do. So what we have is we have a single variable. There's not a relationship here. It's just one idea, and we just want to know more about the mean of whatever it is. Okay? And so I've just got one variable. It's a numerical variable, like a quantitative variable, because I couldn't calculate the mean if it was a categorical variable. Okay, so I've got a quantitative variable, so weight or height or whatever, lung capacity, and the variable would have a name. This is how I do it. And it's a quantitative variable. Okay, and I just want to know more about it. So it's not related to anything else, I just want to know more. So that's the picture in my head. I've just got one variable, I want to know more, and when I see that picture, normally what I would do is I would use the t-test. But the z-test is for this situation, where your data comes from a normal distribution, and you know what the standard deviation of the whole population is. So true standard deviation known. And that is why you never see it in practice, because presumably in order to figure out the true standard deviation for the whole population, you would have to know the mean first, because you use it in the calculation for the standard deviation. So why would you do this? Because you know what the mean is anyway. Okay, so that's what you would do, okay? And that's my picture of it. So the parameters are the true mean. Mu is the true mean of whatever it is. True mean of, insert name of variable here. Okay. Sorry, I need to make sure I write more neatly. Sorry about that. So the mu is the true mean of whatever, and then your null and alternative are mu equals whatever the number is. So there is a number to go in this spot. They normally call it mu naught. Because it's one that goes with h naught. And the alternative, you've got a few options for what the alternative might be. And it would be not equal to, less than, or greater than. Okay? But traditionally you do that one. Okay, so it's like, is the mean equal to whatever the number is? And the answer is either yes or no. And it's a yes or no question, right? And so therefore it's a hypothesis test. The test statistic is a Z, hence the name Z test, which is your sample mean minus whatever you think the mean ought to be from the null hypothesis divided by the true standard deviation of the whole population over root n, where n is the sample size. And when they say, when Rob says, what's the test statistic, he means, what is the formula for it? If he wanted what SPSS spat out, he would say, what is the value of the test statistic? Okay. Now, technically, you could calculate this one yourself. It's perfectly reasonable if he told you what the sample mean was and the standard deviation was and n and mu naught, you could perform this calculation in the calculator. And so it's reasonable that he would ask you such a thing. And the distribution. Concept of distribution is that anything that you could possibly measure or calculate in any situation whatsoever has a distribution to tell you what all the options might be and what the probabilities that go with them are. And the concept is that this Z would come to different answers in different samples, and so they would all have probabilities to go with them. And the one that I get in my sample is however likely that it is, and that's what I'm looking for. So I need a distribution in order to figure out the p-value. That's what it's there for. So Z is distributed according to a normal distribution with mean 0 and standard deviation 1. Okay, so I said that aloud. This is just shorthand maths for what I said aloud. Z is distributed according to a normal distribution with mean 0 and standard deviation 1. Okay? And then once you've got that, you should probably draw a picture of it. So that's your Z that you calculate either there or there, depending on whether it comes out as plus or minus, and your p-value would be the bit outside. So I should say that if you're doing one-sided, so this is how you could add this to the diagram. If your alternative is actually that mu is more than mu 0, so you've got a really good reason to believe that it can't possibly be less than the mean you think it is, and it can only be more, then you put greater than. Okay, so for example, there was one in the lectures, I think, with fertilizer in bags, and you did some process to them, and the only thing that could possibly happen in that process is for there to be less in the bag. You can't add any to it. And so you're interested in whether the mean is still what it used to be or whether it's less, because it can't possibly be more. Okay, that's the idea behind it. So you might also, I should probably put back in brackets, you could also have or HA mu is less than, or HA mu is more than. I will write a neat version of this before I put it online, by the way, but I will put it online. Okay, so that's really scratchy, but maybe I'll put it below. So or HA is mu is greater than mu naught, or HA mu is less than mu naught. They're all options as well. When I did statistics back in the day, I was taught that you should never do a one-sided hypothesis test by my lecturers. And so it gives me great pain to write that because I think it's wrong. But anyway, there we go. Most hypothesis tests won't be one-sided because of that abiding tendency in all statisticians. But they have mentioned it in the lectures, so I need to say it now. Okay? So the p-value for a less than will be over here. So that's the one that goes with the less than alternative. So that's our HA alternative. This area is the HA greater than alternative, and the two combined is the HA not equal to sort of alternative p-value. Okay, that's my picture. See, I quite like putting pictures on cheat sheets because it's not worth the pain, the time of trying to read the words. And that's the Z test. And that's pretty much everything I would put on there about it because that's everything I need to know. Okay, once you've got the p-value, then the same ending is the same. And you can even put that on your stock standard statements. The p-value is less than insert alpha here, and therefore we reject the null hypothesis. So insert context conclusion here. So the mean is not equal to whatever. Okay, so I might add that to my list when I do it so that you can see it. Now that's a Z test for a mean. Okay, so you can imagine writing this extremely neatly, but this big, right, on a cheat sheet. Or you can use Ben's table. Okay, so the next one might be, what's the next one on the list? So I'll just tick that one. Okay. The next one is the T-test for a mean. Also known as the one sample T-test, okay, which is I think what he's called it. That's another option for what it's called. And the question is the same as the question for the Z test. Is the mean equal to some number? And again, it's a yes or no question. That's why it's a significance test, because yes or no questions belong there. Is the mean equal to some particular number? It's exactly the same situation that you have for the Z test, but there's one fundamental difference. You don't know the true standard deviation. So it's the same. There's one new quantitative variable, and it has a name of some sort, such as salt or height or whatever it is, and you want to know more about it. And it's a normally distributed variable, and true standard deviation is not known. Okay. Oh crap, the assumptions. Sorry. Can I go back here? They all have assumptions too, so I need to add that to the list. So the assumptions in this is that the original variable is normally distributed, which I drew on my picture here, right? Normality, which I would check using a histogram. And the true standard deviation is known. That's an important assumption for this one as well. So I don't think there's any more. Oh, of independence. It's always independence. And you could only get that from the story of how the data was collected. There's no way to check independence with a graph. So there's a classic question where they say, use the graphs that are here to assess the assumptions if you can. And you should always say, you know, in the histogram I see blah, 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 so this is reasonable. I cannot check the independence assumption using graphs. Something like that. Just in case, because you want to point out that you know that you can't do it with the graph, because there might be a mark attached with it. Okay, so let's see. Parameters is still the mu, which is equal to the true mean of whatever the variable is. The null and alternative are the same. Or the greater than or the less than as well. Okay, the test statistic is a t, which is x bar minus mu naught divided by s on root n. Difference being in the other one it was sigma, which is the real standard deviation, and this s is the sample standard deviation. And the distribution, t is distributed according to a t distribution with n minus 1 degrees of freedom. What the degrees of freedom means, well, there's two versions. One is the really high-powered maths version, which says that the degrees of freedom is the dimension of the subspace you're projecting onto, which is what Fisher would have said, because Fisher had been the man who invented, well, he didn't invent the T-test, but the Fisher who invented most of stats was a very clever man and knew a lot about geometry, which is what this is based on, and was never made sense to anyone and made everyone feel like an idiot when he talked to them. And the tradition has continued in statistics teaching to this day. But the real, what I say, is that the degrees of freedom, this is the degrees of freedom here. See how it says df? I call it the distribution finder. Okay, because it's just telling you which t-distribution you have to choose from. Because there's this whole list of them, right? One for each sample size. So there's this whole list of t-distributions that when Gossett invented this, he came up with t-distributions. There's this whole list of them. And if we had a nice book, we could find in a book and go to the right one. And we have to go to the n-1th one in the list. So if we had 10 people in our sample, we would go to the 9th t-distribution. It's the address for looking for that t-distribution. That's all it is. And to the naked eye, it looks exactly like a normal distribution, but to a professional statistician, it still looks like a normal distribution, but it's actually different. So it's the same deal, everything's the same. It's just t this time. And your p-value is the same as it was before. And your assumptions, well, normality, which you'd check with a histogram, and independence, which would be the story. Note that you should probably say a little point where you go, if the sample size is big enough, you don't have to worry about the normality assumption. Okay, so he said that in his lecture. So it's sort of like normality histogram, it's sort of like unless n is sort of greater than 30 is the one that he said, or 15, something like that. All right. I should have talked about confidence intervals, but I'm on the track now, so I'm just going to deal with that another time. Okay, doing well. That was the t-test for a mean. Now, we do have one more hypothesis test that belongs to a single sample, and it's not about a mean, it's about a proportion. But as I said, sometimes it's easier to organise things in a different order to the way that they were presented in the lectures, because it makes sense in the lectures to talk about t-tests while you're talking about t-tests. But it makes sense to me to put all the ones that belong with that aren't about a relationship, but are just about a single variable in the same place. So I'm going to do the z-test for a proportion. So the z-test for one proportion, I'm just going to sharpen my pencil. Z-test for one proportion is the same situation again, you've only got one variable and you're only interested in what it's like, but this time it's a categorical variable. It has, you can split it down into a yes-no situation. Your variable name has two categories, and it's a categorical variable. Okay? And what you're interested in with this, okay? What you're interested in with this is, say there's yes, you want to know what the proportion that goes in that Y category is. That's what this hypothesis test is about. You want to know about that proportion. Okay? So the proportion that goes in that category, that's called P. That's the picture in my head for this test. Okay, I've got one categorical variable that has two options which you can call yes or no. So it might be male, female. It might be gets cancer, doesn't get cancer. It might be believes is going to vote for Greens, does not vote for Greens. It doesn't matter what it is, as long as you can classify one of them as your yes and the other one as your no, then you're in this situation. Okay, so the question that goes with it is something like, is the proportion in whatever category it is, but I'll say yes, equal to a particular number? And usually that number is 50%, because in percentage situations that's what you're looking for. Okay? Of course, never write proportions as percentages, because for some reason statisticians think that percentages are evil. Always write them as decimals. So, unless it's a confidence interval, in which case you say 95%. Okay? Which is the one exception to the rule. So, but if it says 50% in the question, you will say 0.5 in your solution. Okay? So that's our question. The parameter is the true proportion, and it's called P. Okay, that's an equal sign there. Let me just see what that looks like. Ah, it's because I'm looking at it on the side. My equal just looked like two dots from here, because I'm looking at it on the side. So I just thought I hadn't written it big enough. The parameter P is equal to the true proportion, and my null and alternative are H0 colon P equals some number. So maybe 50%. That's the most common, because especially in opinion things you want to know if more than half of the people agree with something. Okay? But one of the examples would be rolling a die, and you say, oh, I think that die's not fair, and it's coming up with 6 more often than it ought to, then the P0 would be 1 in 6, because that's what you'd think it would reasonably be. And that's one of those situations where the population doesn't exist yet, because the population is all possible dice rolls. And it doesn't exist until you roll the die. So you can't really talk about having a random sample, but since you know that every die roll is independent, you're okay. That's what I meant in the previous one about populations not existing yet. And the alternative, I think technically there is a more than, less than situation there, but as far as I'm aware, he didn't cover it in the lecture. So we're just going to go P is not equal to P. Because usually it's impossible to tell whether the proportion will be more or less. You just can't tell. If it's opinion, you just don't know. So you just leave it at that. Okay. The test statistic. Well, we've given a hint. It's a Z test. So Z equals... Now I would have to look this up in the lecture notes, I reckon. P hat. I believe that's it. In the lecture notes it's probably just written as a P rather than P0, but I'd like to make everything consistent. If the other one uses a mu0, then I'll use a mu0 here as well. I'll use a P0 here. And the distribution, well, Z means that it's normal with mean 0, 1. Okay? So when they ask distribution, they want precisely a statement like that. So what you want to put in your cheat sheet is something that's approximately what you are supposed to write down when you're in the exam. So, okay. Now technically that's only the distribution if the null hypothesis is true, because you've assumed, the only reason you know what that distribution is because you assumed that the true proportion really was P0. Okay. And what's next? Assumptions, but the distribution will of course look like this. Same for all z's. And assumptions. This version only works for sort of big-ish samples. So I believe it's that NP and n times the opposite of p are both more than 10. Check that in the lecture notes, in that Monday's lecture, that you need, this approximation only works if you've got enough in both categories here.
Brooke said 10, he said 5.
Sorry? He said 5? All right, let's go with 5. So we'll go with what Rob says, because Rob wrote the solutions to the exam, right? Or will be writing them. The exams are only due last Monday, so he might not have written the solutions yet. You would think that lecturers would write the solutions at the same time as the exam, but it's not always true. Okay, so the assumptions are that n times the p naught, so n is the number, and 1 minus n times 1 minus p more are both more than 5. So notice that this isn't based on the data you've got, it's based on what you think the probability ought to be. Okay? The reason that's true is that this is not technically a normal distribution at all, because p can only really be however many out of n, p hat. So that p hat, if you've got 60 people, it can only be 1 out of 60, 2 out of 60, 3 out of 60, 4 out of 60 for that p hat, which means that there's only certain options for what the z could actually come out to. And since there's only certain options, it's not technically continuous, and so it's not technically a normal distribution. But for big enough samples, it comes out okay anyway, so that's why. So, yeah. All right, but that's all the assumptions we need. We don't need to assume normality because the original variable we're looking at wasn't even quantitative variable, so there's no point assuming it's a normal distribution. But technically this is a normal distribution assumption. It's assuming that this is a normal distribution. But yeah, that's our assumption. Okay. You actually do have one more test which works on one variable, and you learned it right near the end. Okay. He did tell you this thing about this +4 thing that you could use for a confidence interval a little later, but I'm fairly sure he won't care which one you use, or he'll just give you something with a big enough sample size that you don't care. So, yes. All right. Ooh. So that's my z-test for one proportion. There is one more that works on a single variable, and it's the chi-squared test for goodness of fit. So do be aware that that's chi and not chi. Oh, well, it's interesting because people can listen to someone talk for an hour about the chi-squared distribution and still call it chi. So I just thought I would point it out because you just don't associate the word with the sound. So I think technically in Greek it's pronounced chi, but we're not going to go there. We'll call it chi. That's good enough. It's definitely not. It's definitely not chi though, because there isn't a ch sound in Greek. So chi-squared test for goodness of fit also works on one variable, because what you're saying is that I have, instead of just 2 categories, I have any number of categories, and I want to know if the probabilities in each category match up with what I think they ought to be. If I was drawing this for myself, I would put the name of the variable there, such as, opinion, or t-shirt size, high, medium, small, medium, large or something. Okay? And I'm interested in whether each of these match up with what I think they ought to be. Okay, so I've got P1, P2, P3, something like that. Usually you're interested in the situation of are they all even, you know? So with 3 you're interested in whether they're all equal to a third in the true population, and it's just that in your sample it's come out to be a little bit different. Okay? So we're saying that there might be a small, medium, large, and you do this big survey and you have a certain number, you've got like 10 smalls and 20 mediums and 10 larges. And you're going, all right, so does that mean, is that statistically different from me getting all evenly for all 3 of them? So how many did I have? 40? Yeah, whatever 40 divided by 3 is. That's what I would have expected to be there if all the probabilities were the same. And so that's what the chi-squared test for goodness of fit is. It says, does what I have fit with what I think it ought to be? So the null hypothesis, I'm just going to do something. And of course, the internet is slow. Or even off. Let's try Internet Explorer, hey? Doesn't even have Internet Explorer. I was just going to go to my uni. Alright, it is here somewhere, though. Just give me a second. Why is there nothing there? No, I'm trying to find the lecture notes, but something is wrong with this computer. I think the internet might be down, like its connection to the rest of the world might be off, which means that the recording is, I should have just gone into Unified, shouldn't I? I'm not going to tell you my username. Not that it matters that much. You get to see what Unified looks like for a staff member. It's only a little bit different. Well, it thinks. I'm just going to fill in some things here because I want to, goodness if it is new this year to this course, so it's never been in this course before. Grindy, grind, grind. I'm going to come back to that one in a second once my uni's done its trick. Okay, but the point is that it's about one variable. There we go. And you see I have a lot more courses than you because people let me see their all sorts of things because I help their students. It does make it really, really annoying that it does a semester 1 before semester 2 at the second year, end of the year. So what I've done here is in the lectures, see how it says the lecture notes? I have put in a file, which is huge, but it's there, of all of the lecture notes all in one file. So we'll let that think for a bit. That's the T. Oh, yeah. Okay. So, the question is are the proportions distributed according to, and however numbers you need. Oh, crap. Distributed according to however numbers you need. So as an example, e.g. 1/3, 1/3, 1/3, for example. Okay? That's the question that's in there. So one of the common ones is are there equal proportions in each in the population? So my null hypothesis, my parameters are the true P1, P2, P3 are the true proportions of outcome 1, 2, and 3. Okay, or however many outcomes there are. You can have 7 or 8 or 9 or 200. Doesn't work particularly well for 200. But it also works for 2, but you're supposed to use the z-test for that. Okay, and then you will have that my null hypothesis, my null and alternative are that mu naught, h naught is that P1 is whatever number you think it is, P2 is whatever number you think it is, P3 is whatever number you think it is. Okay? And h naught is, HA is they are not equal, or at least one of them is not equal. They are not all equal. Okay, so it's a little bit like Anova, where one of them is they're all equal and the other one you just have to use words. And then you'll say the test statistic is a chi-squared. Now with a chi-squared he won't generally ask you to write a formula for it because it's too complicated to describe. But it'll be chi-squared is equal to that for all the i's. That's what it is. It's the sum for all the different categories of the estimated one from your sample minus the one you think it is in the hypothesis squared divided by that. So observed minus expected squared divided by expected. The same with all chi-squared tests. Okay? And so we could actually write it like this if we like. Observed minus expected squared divided by expected. And that's perfectly reasonable. Okay? So these are the expected ones in the null hypothesis. And the distribution will be my chi-squared is distributed according to a chi-squared distribution with n minus 1 degrees of freedom, where n is the number of categories. So I will say number of categories minus 1. Okay, so with this one where there's 3 categories, it will be 2. And that's to do with the fact that the table that you would draw your percentages in has 3 bits, and if you cross out one of them, that's what's left. Okay, so you end up with 3 minus 1, which is 2. So it's to do with the fact that if you knew what 2 of them were, and you knew what the total was, you could come out with what the last one was. So if you had 50 people and you knew that the first one was 10 and the second one was 20, you'd know that the third one would have to be 20 as well. So you can only sort of got freedom to change 2 of them before you know the last one. And that's why it's called degrees of freedom. But it's also a distribution finder. It just tells you that you should go to in this case, the second chi-squared distribution to look up the answer. And so then with your graph, be over there, and it will always be a one-sided one for chi-squared. Because you squared everything, it's impossible for it to be negative, and The only way that you could possibly get 0 is for all the observed ones to be precisely equal to the expected ones. Okay, so, yeah. I think I might have told you something astray there with the expected, because I think what you're supposed to do is you say, well, if I have 30 people, the expected would have been 10, 10, 10, and you actually use the raw number rather than the percentage, but it should work out fine anyway. So it's always over this side. And then your assumptions is the expected are all greater than 5. Not that the original ones are all greater than 5, just the expected ones. Okay? So all of them were for one proportion. And let's just have a look at the difference between them. This one, the z-test, was a quantitative variable with a normal distribution, but we knew the standard deviation. The t-test was a quantitative variable with a normal distribution, and we didn't know the standard deviation. The z-test was a categorical variable with 2 categories, and the chi-square test, for goodness of it, was a categorical variable with any number of categories. Okay, so categorical variables, knowing how many categories there are actually really important to the result of what you're trying to achieve. How are we feeling? Oh, okay, yes, you're right. Let's go right down to the end where he did that. We want the most expected counts to be at least 5. I think that other one was for the, there. That's for the homogeneity chi-square test. So SPSS, when you do a chi-square test, will tell you how many of the boxes have expected count more than 5. So in the assignment, he asks at some point, do you have enough data to use this test? And you look at the bit and there's this little thing and it says 0 cells have expected count more than 5. And so you can say, yes, we do, because they're all less than 5, sorry. 0 of them have expected count less than 5, so we don't have to worry. So you only want at most 20% of them to have expected count less than 5. Okay, so those are all the ones that go with one variable, and everything else is about relationships. Okay, so with relationships, let's start. So relationships have 2 variables involved, and you're interested in how one variable appears to affect another. You can't be sure that it really does, because you can never tell causation unless there's an experiment involved. But you can usually say, well, numerically, this changes in this one correspond to changes in this one. So the first one of those is the t-test, the paired t-test. And in the paired t-test, you're in the situation where you have a categorical variable, and you want to know whether it makes a difference to some quantitative variable. Okay, so the paired t-test is designed for the situation where that quantitative variable has a normal distribution. That's one of the assumptions. And it's also designed for the situation where that categorical variable is not actually technically in your data anywhere. It just tells you how many times you should measure that quantitative variable. So each object or person in your study, the outcome is measured twice. That says out, by the way. Out for outcome. That quantitative outcome, or if you like, response variable, that quantitative outcome variable is measured twice for every person, and the categorical variable isn't really there in your data. It just tells you under what situation you've measured that outcome. So your data will look something like this. Situation A, situation B, and you'll have numbers like that. Okay, that's what it will look like. So that's a paired t-test situation. your classic exam question will be that he'll give you both the mean of just the A's, the mean of just the B's, and the mean of the difference, and he'll say, you know, do the hypothesis test, and you could have technically, if you'd been careful, you could have chosen if you hadn't been careful, you could have chosen an unpaired, like a 2-sample t-test, but it's a hint that if it's possible to calculate the difference, then it's possible to do a paired t-test. So what we actually do with a paired t-test, just to zoom in on this person, we have that outcome number under A, we have the outcome number under situation B, and what we do is we do the difference, like that. We take A minus B. So with my chili example, I have my friends and I give them a meal with chili and I measure their temperature. I give them another meal without chili and I measure their temperature, and I go with chili minus without chili, and that's the difference. Okay? Technically that's what it's doing. And what we're really doing is we've got this new question now about the difference, which is just the difference, which is a quantitative variable, is the mean equal to 0. That's what we're really doing in the paired t-test. Okay? So what we've actually done is we've created a brand new variable and we're asking a brand new question. Okay? Now, the formal name for this for statisticians doing this sort of thing is called transnumeration, where you take your numerical data and you turn it into something else in order to answer the question. So that's what the paired t-test is actually doing. We're not really asking this question at all, though if I look at that picture it tells me I should do the paired t-test because I've got a numerical outcome, a categorical explanatory variable, and it tells me to do 2 measurements on everybody. And go, okay, cool, t-test, that's what it's for. But what we're really doing is this. If everybody has 2 measurements, it must be possible to calculate the difference, and I'm going to look at the difference. Okay? So, the reason I draw this picture is because I understand everything in pictures, but we now start going back here to the question that it answers. Does the categorical variable make a difference to the quantitative outcome? Okay? So does chili make a difference to temperature? And that's how it will be pitched. Okay? And so that's why I draw this picture, right? Because it's saying the categorical variable doesn't make a difference to the quantitative variable. Okay? And it doesn't have to really make a difference, it can just be associated, but that's the picture that you'll have in that's what the words will say. Okay? The null hypothesis, the parameters, the parameter will be mu d, the mean of the difference. Not the difference in the means, that will come to the same answer. It's the mean of the difference. So you calculate the differences first and then do the mean. Oh, there's only 2 F's in difference. Got a bit excited there. The null and alternative. Normally, you can put any number in that spot, but for a paired t-test, you are specifically interested in whether there's a difference or not. Okay, so if there's no difference, the average difference will be 0, because there's no difference. Okay? And then your test statistic, sorry about this. Will be a t, which will be the mean difference minus 0 divided by the standard deviation of the difference divided by root n. Okay, so what we've done is we've said, hey, look, the original variables, actually we're going to convert them all into d, and then all of the statements we're going to make about d, and we're going to do exactly what we would normally do for a 1-sample t-test. And the distribution is the same as it would be for a 1-sample t-test, and the picture that goes with it is the same. And then your assumptions for the paired t-test are fairly special. You know how I drew that normal distribution at the top? I actually don't care what the original variables were. I just care about whether the difference comes out to be normally distributed. So the differences are normally distributed, come from a normal distribution, and the differences are independent. It's really interesting because the paired t-test is actually the simplest one of any of the relationship hypothesis tests that you could ask. Your relationship hypothesis tests can get more and more complicated as they go along, with Anova at the pinnacle of complicatedness. The t-test is the simplest, but it's actually one of the hardest to talk about because you're not talking about the original variables, you're talking about the difference in the original variables. So that's, yeah. So you just need to make sure that when you do your parameters, we'll say it's the mean of the difference. And you should normally actually say whether it's like A minus B or B minus A, whichever way around you think it's supposed to be. Okay? So whether it's before minus after or after minus before, it won't make a difference to the results. It will just be that in one case the T will be over here on the positive side and the other one will be over here on the negative side. But you're supposed to specify. So you might say before minus after. And the before and after is the most common situation. So if you can look at it and think about it in terms of a before and after, then it's probably a paired t-test. So it's usually, that A and B is usually before and after. I need to just put that somewhere. Maybe after and before, right? Okay? Sorry. It's normally after and before. So if you can think of it as before and after, then it must be a paired t-test. And it must be, because you can't do them at the same time usually. So, yeah. There are some special situations where you're actually measuring them simultaneously, because the object under study is not like a single person. It might be a pair of twins, for example, and you measure something on one twin and something on the other. Okay? So it's sometimes necessary to think of your subject not as a single person, but as a blob that's constructed of several different people. Okay. So that is the simplest to calculate, but not necessarily the simplest to do. And then the next one is the two-sample. Did he call it two-sample or independent samples, or do you remember what he called it? Two-sample? Cool. Some people call it the unpaired t-test because it's not paired, or the independent samples t-test. Okay, so your unpaired t-test goes the same. You have a categorical variable and there's a numerical outcome, okay, quantitative outcome. See, my sketches are becoming more and more streamlined as they go along. And your quantitative variable, instead of telling you to measure the outcome twice, it tells you to create two separate groups of people. Everybody's just got this outcome measured once. Okay? And this is supposed to be a normal distribution. All right? So, the question, there's two possible ways of asking it. One is, does the categorical variable have an affect the quantitative outcome? Okay, so for example, does chili affect temperature? Does gender affect height? It does. Or lung capacity. You can also ask it in the sense of, in the two possible categories, are the means the same? Okay? Is the mean of the quantitative variable the same in both categories? Okay, that's the other way to ask it. And this is the one that belongs with, sorry, See ya. Oh, I should just check the recording. Okay. This is the one that the null hypothesis comes from. So you'll get your parameter will be mu A is the mean in category A, and mu B is the mean in category B. He normally does it 1, 2, doesn't he? Oh well. And the null hypothesis is that mu A is equal to mu B, and the alternative is that mu A is not equal to mu B. All right, quickest way to do that. And then we've got a test statistic, which is T, and it has a formula which is complicated. Just looking it up on the screen. X bar. X bar 2, yep. Ah, here they are. Let's zoom in on that. There it is. X bar A minus X bar B on SA squared on NA plus SB squared on NB. And that's a square root there. And the distribution, well, it's approximately a T distribution with the degrees of freedom that is complicated. And you'll get the degrees of freedom from the SPSS output. Okay, if you were calculating this by hand, you'd normally choose n minus 1 for whichever of these is the smallest n. If you do your SPSS output, it'll give you 2 rows, one for equal variance and one for not equal variance, and you're supposed to use the not equal variance one, and it will tell you a degrees of freedom like 54.83 or something. So you'll get that from the SPSS output. And my assumptions: independent between groups, independent within groups, sorry, I'm not doing very well at remembering to do that, independent between groups, independent within groups, and normal distribution in each group. That group means population, technically. You see there's a lot of information here, which is why Ben puts it in a table, but sometimes when you're looking at it as a whole, it's nice to put it on a page, at least for me. So there is one more situation which is similar to that, and which is when you've learned something. The Wilcoxon rank sum test says it's the same situation. You've got a categorical variable which is telling you to measure everybody once. You feel free to leave because I'm just going to yabber on all afternoon. It's going to tell you to measure every variable once, every person once, the outcome once for one group and once for the other group. And the outcome is still a numerical variable, but it's not normally distributed. It's something crazy. Okay? It doesn't have to have 3 humps, it could just be not symmetrical. And that's what the Wilcoxon rank sum test is. The question is the same. Same as two-sample T-test. But you can't write any parameters down. So parameters, there aren't any to mention. Null and alternative H0, both distributions have same location. Both distributions, yeah. They do not. Have the same location. So it's a really general test because it doesn't actually involve the actual data, because what you do is you take the numerical data and you just put everyone in order and you count how many people in group A are above how many people in group B, and if there's more people in group A above group B than there are group B above group A on average, then group A is bigger. So, and that's how it works. So the test statistic, I think it's a W, but we don't even need that from SPSS. Don't worry about it. And the p-value is from SPSS, basically. And we don't even talk about the distribution of the W either, because SPSS figures that out for us. Because it's complicated. With small samples, they'll have a different way of figuring out the distribution as you would for big samples. So it's just too hard, so you just leave it. Okay? And your assumptions, none. It's a numerical variable. Or independence, there's always independence. Independent within groups. Independent between groups. But there's no assumption of normality, because that's the point of the Wilcoxon test. I'm so close, I'm just going to keep going. Even if you leave, I will keep going and record it and upload it. I'm just going to check that my recording hasn't turned off. No, it's still going. And I will write neater versions of this to put online, so that you can check what I meant when I wrote some random squiggle with my doctor's handwriting. Okay. So we're doing well. So far, look, these three, the paired t-test and the two-sample t-test and the Wilcoxon test, those three, were all about looking at categorical variables affecting a numerical variable outcome. So you're thinking, yeah, there's some sort of yes-no, and the outcome that's a numerical is different for the yes or the no. Okay? And it's all based on how you're setting up your data collection, so whether you have multiple records on the same person or whether you've just got two separate groups and you only measure everybody once. And it's also based on whether you think it ought to be a normal distribution or not. But these are all designed for the same overall question of, does this categorical variable, like does the yes or no make a difference to the outcome? That's the main question. And so when I read things that are in exam questions, I look at it and go, okay, it looks like we've got male and female is supposed to affect some outcome. Excellent. It's either the paired t-test, the two-sample t-test, or the Wilcoxon. That narrows it down. And now I can go, yep, we'll just have a look at the histogram. Normal. Okay, so it's not the Wilcoxon. And we've measured everybody once. Okay, so it's the two-sample t-test. Okay, so you can narrow it down like that, which is what his flowchart is about. But I quite like thinking of it in terms of a relationship that we're interested in. So we have one more, well, two more, that have a numerical outcome. Anova. So Anova has an outcome, right? And it also has a categorical variable that's affecting changes in that outcome. You know, small, medium, large. What treatment you gave people. You might give them a placebo and the existing treatment and the new treatment. So, and there can be any number of groups. You might have horses, and you'll give them all different types of feed and measure, I don't know, how often they poo a day, which has happened, right? My favourite one is the rats in the medical suit, where they're trying to figure out how to measure the effect on people's blood supply in space, but they couldn't send the rats to space. And what they did is that they figured out that in space, because there's no gravity, on Earth, because of gravity, your body is naturally set up to push blood upwards against the flow of gravity. So in space, your blood tends to collect in your head because there's no gravity pushing it down, but your body's pushing it up. And so what they thought was if they hung the rats up by their tails, the blood would rush to their heads and it would simulate what would happen in space. And so they had several groups, one which wasn't hung up by their tails, one which was hung up by their tails for a certain amount of time, and another one was hung up by their tails for longer. And another group that was with the drug and one without it. So they had like 5 groups of all these rats strung up by their tails, and then they measured their blood pressure in their heads. So, isn't that awesome? Poor little rats. Anyway, so it's this situation, and we have 3 groups again. This outcome is measured once for each group, like once for each person. Okay? It is actually possible in Anova to have the situation where you put everyone in all 3 situations. You say we're going to measure someone under this situation, and under this situation. So it's like the paired T-test, but there's 3 measurements. You don't do that in Stat Prac I, but it is possible. So this is Anova, that's what it's for, and this is supposed to be a normal variable as well. Cool. So your question... So you've got 2 versions. Is the outcome affected by the category? So does this categorical variable affect the outcome? So it might be, for example, does diet affect bowel motions? Right? Or is the mean the same under all categories? Which is the same question, but specifically focusing on the mean. So my parameters, U1 equals mean in category number 1. U2 equals, and etc., however many of them there are. And then my null. H0 is that mu1 equals mu2 equals, and however many of them there are. And HA is not all means equal. And you can write that statement no matter which Anova it is, because that's the safest way to say it. Because you're not saying that all the means aren't equal, you're just saying that they're not all equal. So it could be that 4 of them are the same and the last one's different. So, but you're not specifying which of those options it is. And then the test statistic. Okay, so the test statistic is an F for Fisher, who invented Anova. And it's difficult to describe, and so they won't ask you for a formula for the test statistic in the exam. Okay, so they won't ask. But you still need to know how it's calculated, so I would recommend in this spot putting a picture of your Anova table. Okay, so there's going to be groups error total, something like that. And then we'll have the sum of squares. It'll have the degrees of freedom. It'll have the mean sum of squares. And then it will have the F, and then it will have the p-value. That's what the Anova table in SPSS or in any stats program will look like. Now these sums of squares are variances, so you figure out how far everything is from the mean, and you square them and you add them all up. That's the total. That's the grand mean. This groups one, you figure out how far each group mean is from the grand total mean, and you add them all up and square them. And this one is each person from their group mean. So the idea being that if you're really far away instead of drawing box plots, I'll just draw dots. So this is where the means are of each group, and the grand mean is here. And so we're saying that, look, if they were really spread out, it would be really hard to tell that they were different. And so you want the spread within these groups to be smaller than the overall spread. So the difference between the groups. So each person here, if I represent them by the mean instead of their actual value, they'd be this far from the grand total mean. But they might be however far from their own mean, and I want to figure out that, look, if there's so much variation in each group that I just can't tell the groups apart because they're just all spread everywhere, then I'm going to get a really high p-value. I'm going to get a low value for f. But if they're all tightly bunched together and the means are far enough apart relative to that, then I'm going to get a high f and a low p-value. So, yeah. In the end, we do know that when you add these two together, you get that one. Okay? So what has been a classic exam question in the past is that they put two of them in and rubbed out the other one, and you'd have to figure out what it is. So you know that those two SS's add up to this third one here. The degrees of freedom for groups is the number of groups minus 1. The total degrees of freedom is the number of participants minus 1. And this is what's left between those two. So this comes out as n minus g. So you can figure out these ones from the situation. You can figure out, if you know two of them, you can figure out the other one of those. And to get the MS, it will be this divided by this. So you'll divide this way. So you'll get SS divided by degrees of freedom. Okay? And then the F is this divided by this, I think. Yes. Because if the error is much, much bigger than the difference in the groups, so if this difference between groups is bigger than the error, you'll get a really big F value when you divide them. And so you'll get a big F value which will correspond to a low P value, which will mean you reject and say that they're different. So yes, it is. I've got it round the right way. I'm fairly sure. Just check that. Yep, I have. So F is these two. You divide them to get the F. So and then the p-value you get from the computer figures that out. So technically, they only need to tell you this one and this one, well, any two of this column and the p-value for you to figure out everything else. I just don't know what Rob's going to do, so I just need to tell you that sort of thing. Okay? And the F distribution looks like this, and you'll colour in that bit there. It looks like a chi-square distribution. There is a distribution. F is distributed according to an F distribution, And with the t, you only needed one number to tell you which t distribution you want, because there's just a list and it goes down. But f has two directions. It's like a street directory. You need to know where you are, which column you're in and which row you're in to figure out which f distribution to use. So you need two numbers, and the two numbers you use are these two degrees of freedom, the g minus 1 and the n minus g. Okay, and the point is that different ANOVAs are different. They can be different in how much data there is in total, but they can also be different in how many groups there are in total. And you need both of those bits of information to figure out which f you need. So it's the f that's in the g minus 1 row and the n minus g column, or possibly around the other way. And the computer technically just subs those numbers into a formula and figures out an approximate answer. So because there's actually no formula for the area there. There's a formula for the height, but the formula for the area is impossibly hard to do. So what it will actually do is use some really fancy approximation method that it just sort of says, well, if I chuck it into this, it'll be accurate to within 10 decimal places. So of course SPSS only does it to 3 decimal places. So, okay, and the assumptions. Well, it's independent within and between, normality, and also equal standard deviations in each group. So the independence, that's from the story, the normality is from a histogram, okay, and the equal standard deviations, you take the biggest standard deviation and divide by the smallest standard deviation, and you want that to be less than 2. Or you have a look at Levine's test in the SPSS output. You take the biggest standard deviation in any group and the smallest standard deviation in any group, and you divide them, and if it comes out as less than 2, you go, oh yeah, the standard deviations are okay. That's technically another hypothesis test, but it's just easier than that. So in the example in the lectures, one of the standard deviations was 8, and the other one was 2, and so it came out as 4, and you go, okay, we've violated that assumption. But of course, he doesn't tell you what to do instead, so it's very unlikely that that situation will happen in the exam because he hasn't told you what to do if that happens. He might say, regardless of what your conclusion is, still do ANOVA anyway, right? But it's unlikely that any of the assumptions will break in the exam. You still need to be able to tell. And that's ANOVA. So let's just have a look at this. ANOVA is different from the others. ANOVA is just like the 2-sample t-test in terms of what we're trying to achieve. It's just that it has more groups to do it on. ANOVA will work for any number of groups. T-test only works for 2. Technically, ANOVA will work for 2 groups as well. But no one does that because more people understand the t-test than they do ANOVA. So, interestingly, that ANOVA has actually been shown to be easier to understand if you teach it right. So, yeah. Okay, and now we are left with 3 more situations. And thank you guys for being so patient with me. So what have we got left? We've got confidence. We've got comparing to proportions. No, I did that one, didn't I? I did 2 proportions. Or did I only do 1? Nope. Okay, so there's 4 more. Yeah. All right, so we've done all the ones with a numerical outcome except regression. And then the only the ones left is that we have things to with proportions, so with a categorical outcome. So I'll do them now. Okay. So that's my outcome. That's my outcome. So now my outcomes are categorical. I've already dealt with one situation where the outcome was categorical. It was the situation where I've done 2 of them actually. I've done the chi-squared test for goodness of fit, and I've done the z test for one proportion. and all the other ones had numerical outcomes, and now, but those ones didn't, it wasn't technically an outcome because I didn't have anything that was affecting it. I just wanted to know more about it. This time I've got an outcome which is yes, no, and I want to know what changes the probability of that. Okay? So I might have a categorical variable over here that changes that outcome. So for example, male and female, men and women, do they have the same chances of participating in volunteer work? So we've got over here male and female, and over here yes for volunteer work, no for volunteer work. And what I'm interested in is the chances of one of those categories. Okay? So this is the Z for two proportions. That's not it, that's a Z. Okay? So, all right. And it is worthy of mention that technically we are still got two separate groups. So this is my explanatory variable, this is my outcome. There is actually a specific test for where you measure everyone twice. So you have a yes-no before and a yes-no after that situation, but you don't. It was in last semester's course. So and the year before. So if you do find an exam that mentions McNemar's test, it wasn't in your course this year. But that's designed. McNemar's test is the paired Z test for proportions. So the Z test for two proportions is this. It's designed for that situation. My question is something of the variety of, is the yes-no outcome, is the probability of yes different in those two groups? That's what it is. Is the probability of yes in the outcome different in both categories of the explanatory variable? Okay? That's my question. So my null hypothesis, or the proportion, okay, not necessarily the probability, but it could also be the proportion of yes. So proportion will do the trick too. And then you can say my parameters, P1 is proportion of outcome in group, category 1, and P2 is proportion of yes outcome in category 2. All right, and then my null and alternative are that P1 equals P2, and alternatively that P1 is not equal to P2. Okay, so it's very, very similar in terms of this part to your unpaired T-test, your two-sample T-test. But instead of means, we're doing proportions. Okay, so we're interested to see whether this yes-no is different, and we only need to look at the yes, because the no is 100% minus that other percentage. So you only need to look at one of them at a time. Okay, so it might be, is the proportion of people who vote green different in two different states? Or is it different between art students and science students? That sort of thing. Okay, so, which it might be. Or it might be the same, right? Depends on the type of science you do, I suppose. So you do any number of questions there. And then the test statistic, which is up here. It's a Z. Which is that. So this P1 hat is the proportion in group 1 that said yes. This is the proportion in group 2. This is the what they call the pooled proportion. Concept being that if the two groups aren't different from each other and they all have the same probability of saying yes, then it's really just one big group. All right? If males and females aren't different, then you're going to chuck them in one big group and figure out the overall percentage that said yes. So that's what it is. It's the pool. It's the overall proportion. So you might have 10% here and 20% here, and if the two groups are the same size, this will come out as 15%. Okay, because you're saying, well, let's lump them all into one big group and figure out how many there are. Okay, and the distribution. Z is from a normal distribution with mean 0 and standard deviation 1, which has its own little diagram, and your assumptions. Well, it's usually something along the lines of independence. Independence between groups and within groups, usually. Technically, the between groups isn't necessary because they might have the same proportion, but and you need that P1 hat times n to be more than 10, I reckon. To use this test when the numbers of successes or failures in both samples is at least 5. Okay? So n P1 hat, n 1 minus P hat, yeah. Are all greater than 5. So technically that's the hard way to say it, that that's actually saying that the number in each category of the outcome for each category of the input is 5 at least. So all combinations have at least 5. Okay. All right, doing well. That was two proportions. Done that one. All right, so we have two more that have a categorical outcome, which are actually the same. Does he call it independence or association? Independence. Your chi-square test for independence is the same situation as the Z test for two proportions. It's just that you can have any number of categories in both the explanatory variable and the outcome. So this is something like, I don't know. This is a really mundane example, but people with different ethnic backgrounds will they have different t-shirt sizes, which they should because there'll be different heights on average. But it's the same sort of idea, but it could be anything. It could be, and you can have two in any number of these categories. You can have two here and two here. But usually it's obvious that one of them is an outcome and the other one isn't, but it doesn't really matter. It could go the other way. And if you can't tell, it doesn't matter. So for example, the one in the assignment is the marriage status, first marriage, second marriage, not married, and whether that makes a difference to health insurance status, for which there were two options. Okay? And I'm pretty sure your health insurance status is not the one that actually causes your marriage status to change, so I reckon that's around the right way. So, so it could be anything. So, is R these variables related? Are they associated? Are they independent? Okay. And note that that question doesn't really have implicit in it a direction that they might be related in. Technically, what you could ask is are the categories in the outcome, are the percentages of people in the outcome the same across all the other categories of the explanatory variable? But that's what the chi-square test for homogeneity is for. So your parameter, actually we're not going to mention them. No parameters to mention. Your null hypothesis, H0 is that there's no association. HA is there is an association. And your test statistic I'm writing the word. Your test statistic is a chi-squared, which is the sum of your observed minus expected squared over expected. So, yep. If you want to know more about chi-squared, actually last year I did talk about it in the revision seminar, but I do want to say one thing about the degrees of freedom. The distribution is a chi-square distribution with a degrees of freedom that goes in this spot, right? There is a degrees of freedom. You have to find which chi-square distribution it is. In the lecture notes, he says that distribution, that degrees of freedom is number of columns minus 1 times number of rows minus 1 in your two-way table, which is true, perfectly true. So it's df equals number of rows minus 1 times number of columns minus 1. But there's a much easier way to figure it out. So that's number of rows minus 1 and number of columns minus 1. And you multiply those two numbers together. And there's an easier way of figuring it out that goes, you look at your two-way table, which has however many rows or columns that it has. All right. So this is my, one variable, and this is the other variable. And then you'll be putting your totals in around the edges. Okay. So this is total. And then this here is the grand total. So this is your two-way table, right? And you figure out your expected number by going, well, the total in the row you're in times the total in the column you're in and divided by the grand total. But to figure out the degrees of freedom, you should just cross out one row and one column, and the number of boxes that is left is the degrees of freedom. So this has got 3 rows and 4 columns, that one, and I have 6 boxes left. That's the degrees of freedom. Because rows minus 1 is 2, columns minus 1 is 3, 2 times 3 is 6, but I don't want to have to do that. I just like to look at my two-way table and cross out one row and column and count how many boxes there are. Number of boxes if remove one row and one column, not including the totals, of course. So this one I have degrees of freedom 6. If I had a 2x2 table, the degrees of freedom would be 1, and that just, I know it's simple, but it reduces stress. So yeah, and that's whatever degrees of freedom it is. So in this case, the degrees of freedom is 6, because I'll cross out that row and that column and I'll get 6 left over. Point being that if I kept the totals the same and I filled in all those boxes, I'd be able to figure out what had to go in the missing ones. Okay, so if I knew what this total was and I knew what these 3 were, I'd be able to figure out what that last one was. So if I can fill in 6 of these boxes before I know everything, that's why there's 6 degrees of freedom. There's 6 things I can change before I know everything I need to know. Okay? and then the chi-square distribution is the shape that it is. And I think the assumptions here, that's all there is, right? That people are independent from each other, right? Yeah. The individuals are independent. Not that the variables that are measured on them are independent, but the people are independent from each other. How are we doing? Wow, I'm really going to have to go home shortly. That hasn't been changed for daylight savings, has it? Okay. Now, the chi-square test for homogeneity is more or less the same. Pretty much. Your chi-square test for homogeneity. Your chi-square test for homogeneity is the same situation. Precisely the same. Everybody has one measurement on them. But your question is ever so slightly different. It is the distribution of the outcome different in the three different categories? Is the distribution of the proportions in outcome different in different categories? Okay, so it's the same question really, because if this variable doesn't affect that variable, then it doesn't matter what the category input is. It's the output category that comes out to that comes out the same every time. It doesn't matter what you put in. So it's the same question. It's just pitched in a slightly different way, and that's why it's called the chi-square test for homogeneity. So up from this point, same as independent. As the independent version, except that the assumptions are individuals are independent within groups. Yeah. So I'm not sure I believe in calling them different names, but your lecturer does. So that's where we go. So that's actually all the hypothesis tests except one, which is hidden in regression, so I'm going to do it as well. Regression has a hypothesis test in it. Regression is specifically designed for the situation where you have two numerical variables related to each other with your lovely scatter plot. And to ask the question of, is there a linear relationship between these variables? Is there a linear relationship? Technically it's just, is there a relationship? You've already established by drawing your scatter plot that it is a linear relationship. Is there a relationship? That's your question, between these two variables here. So you know height and FVC in the current assignment. The parameter is, does he call it alpha A and B? What does he call it in regression? Or does he call it beta naught and beta 1? In the Prac it's called beta naught and beta 1. Yeah, we'll just call it beta naught and beta 1. So the parameter is the true slope of the line which is beta 1 as per y equals beta 0 plus beta 1x. Okay? So it's the true slope of the line beta 1 as described in this equation. That's the parameter we're looking at. Okay? And we're interested in whether there really is a relationship between y and x. So this is telling us, knowing x, we can estimate what y ought to be. That's what this says. If this is 0, then knowing x doesn't tell us anything about what y ought to be. It's just going to be equal to beta 0. That's going to be our best estimate. Okay? So my null and alternative is that beta 1 is 0. So if beta 1 is 0, there'll be no relationship. If beta 1 isn't 0, then there is a relationship. The test statistic is a t, which is b1, which is the estimate from the regression, technically minus 0 because we're comparing it to this 0, divided by the standard error of b1. And you get both of these from the regression output. So and here's the key. The distribution is that t is distributed according to a t distribution with n minus 2 degrees of freedom. So for an ordinary t-test, it's n minus 1. For regression, it's n minus 2. And it's to do with the fact that in order to figure out what B1 is, for B1 is you have to simultaneously figure out both B1 and B2, and so you lose 2 of the degrees of freedom. Whereas when you're just doing it with an ordinary single mean, you only have to find the mean, because there's only one parameter involved. Even though we've only got one parameter involved in our hypothesis, there's 2 parameters involved in this situation, which are here and here. In a mean situation, there's only one parameter involved in the whole scenario. But in regression, there's 2 parameters involved in the scenario, so I have to take 2. And assumptions, independence, which is from the story, linearity, which is from the residual plot, homoscedasticity, which is also from the residual plot, and normality, which is from the histogram. That is all of the hypothesis tests in Statistical Practice I. I might go home. Thanks for sticking around, and thank you whoever is listening for sticking around. Look, if you've got any more questions, come to the Maths Learning Centre and we'll talk some stuff through with you. Good luck on all the exams between now and Stat Prac I, and on Stat Prac I as well, but I know that it's not the first one, so good luck on all of your study, guys.